Okay. You know what time it is. Questions. I possibly may have answers. Yeah.
Is it safe to assume that there's a
No.
distribution out of 9 questions, 3 from the first midterm, 3 from the second midterm, 3 from new material?
That's not that far off. Yeah.
Yeah.
What? What? I didn't hear you.
How many questions are from each section?
I can't say that. But it's roughly equal across everything. Yep. No. No multiple choice. But the first question is, so I give you a bunch of languages, and then you say, what is the most restricted? So I talked about this last time, for those who are hearing this for the first time. You put the language that is the most restrictive for that particular language. So if you have a language that's regular but not finite, then the smallest categorization for that language is regular. If I have a language that's decidable but not context-free, you have to put decidable. But if you have a language that's regular and it is also context-free, what should you put? Regular. Because it's the most restrictive one for that. Okay? Yeah.
I'm going to use one of your daily exercise questions.
Okay.
The TM model where we are not allowed to write at
Mhm.
the end of the input.
Yep.
Can we show that? It says prove that we can decide whether a given TM in this model with an arbitrary string accepts that string.
Yep. So what did we call models that you can't move past the end of the input? LBA. So is A sub LBA decidable? Yeah, we showed that.
That's fine. Okay.
Yeah, I asked that question before that lecture because I wanted you to think, how could we decide that? Well, it's just that there are only a bounded number of configurations that there could be. So we can't run longer than that. Other questions? Yeah.
Can you quickly go over some of the closure properties for regular languages, context-free grammars, decidability?
Mm-hmm. So every single one, right?
Yeah. Just quick.
Okay, so let's put what is the middle ones? Complement. I think these 5 are fine. So let's make a handy dandy table. So for regular, which of these 5 are regular languages closed under? All of them. Yep. Good. What about for CFL? Union for sure. Yep. Not intersection. Good. What about concatenation? Yep. For concat, yes. Because just take the 2 grammars for the 2 languages and say the start variable, the first is S1, and the start variable, the second is S2. Make a new rule with a new start variable S going to S1, S2, which is the concatenation. What about star? Yep, because it's just repeated concat. Complement. Nope, good. Decidable. Yeah, union. Intersection? Intersection. Yes, intersection. Yes. Yep, just run the decider for both machines, Since they run in a finite amount of time, answer if and only if both said yes. Concat.
Yes.
Yep. Star.
Yes.
Yep. Complement.
Yes.
Yes. Recognizable. Union. Yep. Although these are not as trivial as decidable, but it's almost the same. Yep, concat's true. What about intersection? It's almost the same as union, but just swap out or for and. Yeah, but could I just say run the first recognizer on the input, then run the second recognizer on the input? I can't do that, right? But how do I do union then? And do it in parallel. Run one step on both machines. Check if either accepts. Then run one more step. Then run one more step. And then therefore you get a recognizer for the union. Star. Yep. Complement. No. Good. What's an example of something that's right here? That ATM is recognizable or is not recognizable? Is recognizable. And how do we know that ATM bar is not recognizable? If it were, it would be decidable by the result that we proved. Good. Any questions? Answer your question.
Yes, thank you very much. What about P?
What's there?
What about P and
PDA?
P's?
Oh, good, good. P and NP, good. Well, if I filled in entries of this table, what would happen? Yeah, what would happen? Then I'll give you homework answers, so. Well, actually, we actually do know the answers because the question says show that they're closed. Yeah, so I might as well just undo these. I won't tell you how to do it, but. Yep, so what is P closed under? Union, intersection, yep. Concat, star, complement? Yes. Why yes? Well, that doesn't imply complement though. There's another class of languages that is closed under complement, but is not closed under union or intersection. But if it was closed under intersection and complement, then it's closed under union. If you have both operations on one side, then you get the one on the other side. But if you have one on either side, that doesn't imply anything about that one, the other one. What about NP? Union, yep. Intersection? Yep. Concat? Yep. Star? Yes. Complement? We don't know. Because it says if we can show that it's closed under complement, if we show it's not closed under complement, then P does not equal NP. So in fact, this entry, we don't know the answer. We conjecture it's not closed under complement, but we don't know. Okay, so should I just put that last one as all 9 questions? All right, no. Okay, is that good? Yeah.
On the first question where we have to find the use restricted
Mhm.
cases,
Mhm.
is P and NP going to be a part of that?
No.
Nope.
P and NP are only part of the bonus question.
Cool.
They won't show up on any of the other 8 questions. Okay? Other questions?
And we only have to decide the only category that is going to be an answer. We only decide.
I didn't hear you. Guys.
Like the only category that we can place those languages on will be this one. Like no other language is part of this one.
Well, there are say like non-regular languages or non-context free languages or languages recognized by LBAs, for example. Right? So, but we didn't really cover closure properties, so it won't be on that.
Is there even possible to have another form for just undecidable or recognizable?
I mean, we could, but it's not gonna. It's gonna be like not closed under for all of them.
Okay.
Yeah. Yeah. So unrec. Are there two non-recognizable languages for which their union is recognizable? So I'll give you an example. EQTM and EQTM bar end up being is not recognizable, and its complement is not recognizable either. But what's their union? What is a language and its complement union? Everything. Well, what is that? It's regular, so therefore it's recognizable? Yeah. Yeah. So it's not closed under union. Because EQTM is not recognizable, EQTM bar is not recognizable either, but their union is sigma star. And so therefore it's recognizable. For this, if you pick the exact same two languages, their intersection's empty, which is also recognizable. I'm not going to go through an example for the next two, but I say that they're both not closed under them either. And what about complement? It's not closed under that either. ATM bar is an example. So unrecognizable is not closed under anything, it seems like. Okay? And undecidable, whoever asked it, is almost exactly the same as this. Let's see, undecidable. So the same two examples will work for union and intersection. So might as well do it. If you pick the exact same two examples, it'll show those. If you work through it, the same two examples for the ones you did for concatenate and star will also work for undecidable. What about complement? Could you have an undecidable language whose complement is decidable? No. So it is closed under complement. Yep, so that's pretty much the only difference. And not regular and not context-free are almost exactly the same as this. So I invite you to think about if there are any differences. Okay, other questions? I mean, I can talk about why the sky's blue. Yeah.
For the exam, will you ever make us move the Turing machine all the way to the right to solve the problem?
What do you mean all the way to the right?
I mean, not Turing machine. The Turing machine, like, you know how like there are some ways where you pretty much make the start one blank and then you save output to the end to like do it. But then there's another way to do it where you like have the first move it all the way to the right and have it to blank at the beginning part of it to solve it. Will you ever make us we'll use that scenario to solve the problem?
Do you think I'm going to ask about making a Turing machine diagram?
No.
I have to grade these in 2 days. So there are no Turing machine diagrams of any kind. No Turing machine diagrams. Okay? But if I happen to have that, then however you want to solve the language that you're considering there's many ways to solve it. Like for the one on midterm 2, there were at least 10 different approaches I saw, all of which were correct. So yeah, Yeah, it's however you want to do it, or whatever's most convenient. Other questions? Yeah.
Can we do more CFL pumping though?
Okay. Any example you have in mind?
One's very similar to the one's going to go inside.
No.
I don't have a specific example, but just like the which one? The power one. Yeah. That's
Yeah, choose again. Okay.
Or yeah, like the one that was on the.
Well, that one's actually very similar to this one, so might as well do this one.
Okay.
Okay. So, if I happen to say prove L is not a CFL, then what do we do? Assume it is. Great. So assume L is, then what? Yep, there's a pumping length. Super duper. Now what? Pick a string with what two properties? In the language and length at least p. If I happen to have a question like this and you don't do that, I'm going to come hard down. Come down on hard on you. So what's the string that has length at least p and is in the language? 0 to the 2p. Sorry. 0 to the 2 to the p. Yeah. Well, it certainly is in the language. Is it length at least p? Well, let's see. If p were 0, what is 2 to the p? 1. So that's good. What if p were 1? It'd be 2 in length. And if I increase p by 1, it's going to double every single time. So p is less than or equal to 2 to the p. So therefore, this has length at least p in length. And it's in the language, so we're good. The string may or may not work, but it is some string in the language with length at least p. So let's work with it. Well, what do we got to do now?
Find every decomposition of the
Yes, look at all decompositions. Subject to what? So W into U, V, X, Y, Z, such that what?
EXY
Mm-hmm.
is not longer than P.
Good. Yep. What else?
VY
Vy is non-empty.
and then UVCI, XYZI,
Mm-hmm.
Z
It has to be in the language. Good. For one eye or every eye? For all eye. Good. Well, what do I know all decompositions look like? Well, U has some zeros, V has some zeros, X has some zeros. Am I going to ever hit anything other than zeros? No. So we know that whatever VXY has, it has some number of zeros, right? Well, could it be 0 zeros? No. Could VXY have 0 characters? No. So let's say that VXY is 0 to the A for A at least 1. I don't know. No, let's make it VY. Because since the entire string is zeros, it doesn't really matter where in the string I pump, right? I might as well just pump at the beginning, but it actually won't matter here. But I'm saying here is since VY is non-empty, if I pump in another copy of v and y into the string, so pump up, then how many characters of 0 did I just add? A of them. Well, let's see. So if we pump up, then how many characters does the whole string have? Well, how many did I start with? 2 to the p of them. And how many did I just add? A of them, plus A. So this is equal to, if I pump up once. Could 2 to the p plus A be a power of 2? Well, A could vary, right? It could be that this happens to land on a power of 2, maybe. Well, let's see. Well, could it be equal to 2 to the p by itself? So could 2 to the p be equal to 2 to the p plus A? No. So it's a strict inequality, right? Because A can't be 0. So it can't be equal to that power of 2. Could it be equal to, say, the next one? Well, what is the next power of 2? Yeah, 2 to the p plus 1. Well, plus 1 in the power. So let's see. Let's compare these two values. Well, what is the largest that, yeah, go ahead.
Is that 2 to the p plus A or is that
Oh, my ambiguous handwriting. Yeah, because that's the length of the string that we just got from pumping up once. All right, well, could these be equal? Well, I'm going to move this over a little bit. What is the largest that A could be? P, because of the first condition, which says that Vxy has length at most P. So this is at most 2 to the p plus p. Right? Well, could 2 to the p plus p be equal to 2 to the p plus 1? Well, what do we know from above? We know from above that p is less than or equal to 2 to the p. No, we can actually say something better. It's actually strictly less than 2 to the p. It's never equal to it. So I think that 2 to the p plus p is strictly less than 2 to the p plus 2 to the p for that reasoning. Right? Because p is strictly less than 2 to the p. Oh, what did I just make? 2 to the p plus 1. So let's see. It can't be equal to 2 to the p, and it can't be equal to 2 to the p plus 1. Is there any one in the middle? No. So could it be a power of 2? No. So therefore, we know that this string is not in L, and then therefore L is not a CFL. I think this is problems also a solved exercise in the book. It may be in the text, but I would take a look at it again if you didn't quite understand the proof. But the idea is that we're trying to say what is the smallest length it could be and what's the largest, and prove that consecutive powers of 2 are outside that.
Could you repeat what you said about looking at both sides of it, saying like it's not, can it be 2 to the p plus 1, and is there anything between?
Yeah, well, because it's the next power of 2, and it's strictly contained between them. So it can't be, it's not equal to either, and it's strictly between them. It's the same kind of idea as when we proved that perfect squares were not regular. So it's the same idea here. We're just showing that it's, 2 to the p plus 1 is the smallest it could be, and it can't be equal to the next power of 2 either. Okay? Other questions? Yeah.
Actually, never mind. Sorry.
Other questions? Yeah.
I found a problem from your last semester's presentation session,
Mhm.
and it was write a high-level description of a TM to recognize 0 to the Fibonacci number, where f then is the n Fibonacci.
Mm-hmm. Okay. You want me to go over that one?
Is it gonna be on the test?
You want me to go over it?
Yeah.
All right. How many of you do not know what a Fibonacci number is? If you don't, get out now. So remember that, let's index it from 0. So f of 0 is 1, f of 1 is 1, and f of n is f of n minus 1 plus f of n minus 2. You may or may not include 0. It actually won't matter here. Yeah, so it's an ambiguously defined, but we're not worried about that here. All right, so how would I write a Turing machine to, or a high-level description of a machine to do this? Well, what we could do is, if I happen to keep f of n on one tape, f of n minus 1 on a second tape, and f of n minus 2 on a third tape, could I add these two bottom tapes and put it on the first tape? Yeah. So once I do that addition, what do I have to do? I got to move the first two tapes down one tape. Okay? So, I mean, let's see. So I'm making this up on the fly. Step 1 is check if a single 0. If so, accept, because that's the 0 and 1 case. So let's initialize a counter n to be starting at, let's say, 2. That actually won't matter. Let's put 0 here. So so there's something we need to worry about. Well, I'm making sure that I'm checking the input that's given to me has Fibonacci length or not, right? Well, if I destroy that input, then I can't decide anything, right? So I'm going to have a single tape that has the input preserved and never changes it. Then I'm going to have 3 more tapes, one of which has f of n, then f minus 1, n minus 2. So I'm going to have while n at least 0. So let's do step A. So we're going to add f of n minus 1 on third tape and f of n minus 2 on fourth tape, and write to the second tape. Then move or copy second and third tape contents to third and fourth tapes. And at each step, we better increase n by 1. Yeah, overwriting the existing contents. Yeah, it's just a high-level description here. But could this program as is run forever? It actually does run forever, right? So let's see. Let's say that the input's length was 17. And I'll let you know right now that 13 and 21 are Fibonacci numbers. Well, if f of n happens to be 13, have I put enough computation in so far? No. What if I reach 21? Have I put enough computation in? Yeah. If I keep doing more, will this 21 ever come back down to 17? No, because the Fibonacci sequence always increases. Okay? So we need to make sure if f of n ever is strictly larger than the input, the first tape's contents, we reject. Because we'll never hit that again. So if f of n has same length as first tape, which is the input, we should accept. Because we just showed that it was a Fibonacci number. If f of n has, I should say, strictly larger length than first tape, reject. And then now we can guarantee it runs in a finite amount of time, because in a finite amount of time, I'll have f of n eventually either being the same as the input's length or strictly larger, because the input's length was finite. Yeah.
Substep C, that just means go back to A.
No, that it just increment n by 1. Oh, you thought that was an up arrow? Yeah, sorry. Curse these ends. All right. But the idea is clear, right? So yeah, just remember, I'm keeping my input preserved because I want to check if the current Fibonacci number is either equal to that or strictly larger. Then I just have some number of tapes which keep track of the existing work. Okay? Any questions about that? And we didn't even need to say tape contents, right? Because since it's a high-level algorithm, we didn't need to worry about tapes here. You got a question?
Yeah. What happens if n is 1?
So
Would you get n minus 1 and n minus 2, and you get negative 1 and something like that?
yeah, so that's what I was worrying about earlier. You should make it 2. But it's a implementation detail. Yeah. So I could have said like repeat until, so I set like a Boolean variable to be false and make it true if f of n has the same length. Yeah. Other questions about this? Yeah.
Since you said there won't be any the diagram, is it safe to assume that you might want a higher level description of the TN?
What do you think?
He's not going to tell you.
Other questions? Oh, a thing about P-set 5. We'll release solutions exactly at the due date so that you guys get solutions of P-set 5 as soon as possible, which could be helpful. Other questions, though, about other stuff? Because we still have half an hour, yeah.
So, in regards to this problem, you mentioned that this is a high-level description. So what would be considered a low-level?
Yeah, this is kinda in the middle. So for it to be a high-level description, I didn't have to say how many tapes I had or whatever. So this is kind of in the middle. For a low-level description, it would be more like scan right until you see a blank symbol, then on the third tape, write a 0 every time you see a 0 on the third tape, and then stop when you hit a yeah. So in that case, you're saying what's happening on the tape. Here, so you see we're kind of in the middle. We're saying like what we're doing with the tapes, but we're not saying what we're doing on the tapes. So yeah, so a high-level description would be here, add f of n minus 1 and add f of n minus 2 and store f of n. So I'm not saying where on what tapes they're being stored.
So would this be considered wrong then for
You're never ever wrong by including more detail. But
if you left stuff out, like
yeah, then yeah. So think of low-level description as being like you could translate it easily into a Turing machine diagram, and high-level being you can easily transform it into a low-level. Yeah. Other questions? Yeah, we still have like 25-ish minutes.
So that's just to re-clarify. That seems to make high-level languages or high-level descriptions not simple to write, but I mean, like we're really just we don't have to care about the tapes.
Yeah, you don't.
Yeah.
Yeah, you don't. Yeah, as long as you're doing a finite amount of work in a finite amount of time, then pretty much anything's fair game.
Cool.
Yeah. Yeah.
Would you say the problems on the final, like, take a class during the same amount of time to do as like the problems we have on the district?
They're designed to be exactly the same, because 5 problems for 75 minutes. If you scale it to 8 problems without the bonus, is 120 minutes, and you have 125 minutes. So it scales exactly. So I designed it to be exactly the same amount of time. Yeah. Other questions? Yeah.
Can you
Sorry. Yeah, so just make sure to budget your time well. Yeah.
proven decidability for M is a DFA and has these small palindromes.
Mm-hmm. Okay, yeah, that's actually a good problem. So this language, so I think I called it PAL DFA, right?
You didn't give it a name, but yeah.
Okay. DFAs are our pals. M is a DFA, and L of M has at least one palindrome. And I claim PAL DFA is decidable. Well, let's see. Well, is the language of palindromes regular? Well, it depends on the alphabet that you use. If it's unary, then that's just even length strings. But if it's, say, 0, 1, is that regular? No. Is it a context-free language? Yes, and we've seen how to make a grammar for that. Well, could we use the fact that it is a CFL, therefore has a PDA or a grammar or whatever, to help us here? Well, let's see. Suppose that L PAL is language of pals, palindromes. So then what is L PAL intersect L of M? Well, whatever this language is the set of strings that are palindromes and the machine accepts, right? Well, if I can answer whether whatever resulting language this is non-empty, is either empty or not. Did I just answer whether or not M should belong to PAL-DFA? I'll say that again. So whatever this language is the set of strings that M accepts and are palindromes. So if it's non-empty, what should I say? Except. Because I just determined there's at least one palindrome in there. Okay, fine. So what can I guarantee about that language? Well, it's a context-free language, intersect a regular language. Oh, what is that? Well, it was definitely decidable, but what else? It's context-free. Okay, this is a CFL. Could I test emptiness of a context-free language? Yeah, and what decider did we see for that? ECFG. Okay, so let's use ECFG. So let's make the actual decider. So on input M is a DFA. Then construct let's do CFG to make it easier. Let's make a CFG G for the palindromes over M's alphabet. Because I have to have the same alphabet as M does. Now what do I do? Yeah, create a CFG with what language? Yeah, and M, good. CFG, let's call it GPAL with language L of G intersect L of M. How do I know I can do this? Where did we see an algorithm for taking a CFG and a DFA and producing a CFG for it, for the intersection? Where did we see that? It was on one of the P sets. It was one of the bonus questions. But I also outlined in class a way of doing a PDA and a DFA, and because it's just like a product construction. Is that any different if I did it with PDAs instead of CFGs? No, because they're equivalent. So we can certainly use a PDA and convert the resulting PDA back into a CFG, but we can do it directly as well. So that's good. Now what do I want to know about GPAL? If it's empty, so what should I do? Yes. Run the decider for ECFG on the description of GPAL. Well, let's say that the name of the decider is D. Could D run forever? No, because it's a decider. So there are two cases. If D accepts and if D rejects. It'll turn out we swapped the answer here, but let's see why. Well, if D accepts, it says, yeah, GPAL, your language is empty. Sorry, pal. Well, if GPAL's language is empty, what does that tell me about G and M? There's nothing in common. So what does that tell me about M originally? There's no palindromes in it. So what should I say for my machine for PAL-DFA? Reject. Good. It's going to be accept here as well, but let's go through it again. If D rejects, that says, yeah, GPal, you have some string in your language. Okay? Well, if there's some string in GPal's language, what do I know about G and M? They have some string in common. Oh, what does that tell me about M originally? There's at least one palindrome in its language, right? So what should I say for my machine for PAL-DFA? Except. Yep. And that's the whole thing. So is that all I should do for this machine? What should I justify about this machine? That it runs in a finite amount of time. So let's make sure. Does step 1 take a finite amount of time? Yeah, because there's only a finite number of characters, and so therefore palindromes there's only a finite number of rows for that. CFG GPal for step 2, does that take a finite amount of time? Yeah, because it's just a product type construction, and we know that product type constructions take a finite amount of time. Step 3, what about it? It's also decidable. It also runs in a finite amount of time because by assumption it does. Step 4, that's pretty easy. So this machine runs in a finite amount of time. Okay. So the reason I like this problem so much is that I usually intend it to be you start off with a PDA and you convert to a CFG. So you have to know equivalents of PDAs and CFGs. You have to know the product type construction for PDAs and DFAs. And you have to know that palindromes is context free. And yeah, that's it. Yeah, so I like problems that tie in a lot of things together like that. Yeah. You should justify it, yeah. Unless it's like incredibly obvious. Like run this decider and if it accepts, then do this. So like that would be really obvious, but here like the first 2 steps aren't totally obvious. So yeah.
How do you think about step number 2 machine? How does that make sense?
Because we saw on one of the problem sets that you can take an arbitrary CFG and a DFA and do a product type construction to make a CFG for their intersection. We also saw in class, I outlined a method to have a PDA and a DFA and make a PDA for the intersection. But you can just convert to a CFG because we know they're equivalent. Yeah. I don't know what the question is. Because it's a DFA. Mm-hmm. Other questions? Yeah, sure.
We've shown that we can show undecidability, that we can reduce an already undecidable problem.
Mm-hmm.
So prove that something is decidable could be a problem that we know is decidable and sort of build up the problem that we can see is decidable.
Yeah, it's just like this. We know ECFG is decidable, so we can use that to make the decider for this thing. Yeah. Yeah, that's commonly how we do it. Yep. Other questions? Yeah. Not recognizable? How do we prove something's not recognizable? Well, there's no. well, yeah, that is the first step actually. But what is the general framework that we did for that? Reduce a known non-recognizable problem to this one. So, for example, we showed last time I think that we reduced ETM, which I told you was not recognizable, to EQTM. So we assume that EQTM is recognizable. Then we can make a recognizer for ETM. But since we know ETM is not recognizable, EQTM can't be either. So it works exactly the same way as for showing undecidability. But you have to start with something that's not recognizable at the beginning. Okay? In class and potentially in the book, yeah. Yeah, sure. You were next.
I forgot my question.
Kind of using this problem, what would be the most restrictive class of languages on this one? Would it just be decidable?
Yeah, because you could construct really, you can construct really hard, encodings of DFAs that are not, so therefore it wouldn't be a context-free language.
Okay.
Yeah. And it doesn't really seem easy to make this on an LBA because it seems like you need extra room to write it. That doesn't prove it, but you won't need to do that. Yeah. It won't be that, it'll be pretty clear which one it has to be.
Okay, that's good.
Yeah, yeah. If you know the closure properties and what the languages actually are, it shouldn't be any surprise.
Okay.
Other questions? There's more questions over here.
Can we just briefly mention why Rice's theorem would break apart on that? Is it it requires a TM at first? Right?
Breaks apart on.
Why on PAL DFA?
Well, because it's decidable, and it's for DFAs.
And for DFAs.
Yeah.
If we looked at it,
If we look at PAL TM, where M is a Turing machine that has at least one palindrome, that's undecidable by Rice's theorem.
okay.
Yeah, because that's a non-trivial property of Turing machine languages. Because if you have two identical languages, either they both have at least one palindrome or neither do. And if you can make an example of one that has no palindromes in it, say the empty language, and one that does have at least one palindrome, say everything.
Okay.
Therefore, it's a non-trivial property.
Oh, awesome, cool. So it's solely because it's a DFA.
Yeah.
Because Rice requires Turing.
Mm-hmm.
Very cool.
Yep. Yeah.
So in the example, when you say that we should prove something is undecidable,
Mm-hmm.
okay, if I see that I can use Rice's theorem,
Mhm.
I can use it, or you have to say
Please do. Yes.
So much easier.
Yeah. But if you can't, then obviously you can't. But if you can, please use it because it's a lot easier to apply it that way. Mhm. Other questions? Yeah. Produce a recognizer for it. Yeah, you could use an enumerator too because we proved that they're equivalent. So you could produce an enumerator as well. Mhm. Other questions? No other questions. Yeah. Sure.
For question 4, would you think the best approach is to just go straight from like the definition of like NP?
Yeah. Mm-hmm. Yeah, show us an NP, show us NP hard. Mm-hmm. Yep. Other questions? Yeah.
How would you prove the sky is blue without examples?
Well, how would I prefer what?
How would you prove the sky is blue without examples?
Start by assuming that it is.
Start by assuming that it is, and yeah.
It's not blue though, so you can't prove it.
It's only blue in the visible spectrum. The visible spectrum is tiny compared to. We still got like 8 minutes, so. Plus office hours afterward, so.
Can we do an example of regex to anything?
Oh, sure, sure. We haven't done one of these in forever. Okay. So here's a regex. I want to make an NFA for it. So what do I do?
Step 1. Make one for 0, 1 for 2.
Good. So I make one for an NFA for 0, 1, and 2. 2's not the arrow, right? Okay. Easy.
Step 2. Make 1 star.
Just wait for everyone.
Yeah.
Okay. Now what do we do?
Follow the order.
Well, it actually won't matter in this case, but which one should we make first? 1 star, let's say. So let's make one for 1 star. And how do we make it for 1 star? Yeah, with the 1 that we have here. So we build off of the previous NFAs that we make. So let's put this in orange. And then, so how do we make the star of this guy? New start state with what? Yeah, with an epsilon in and its final. What else? Yeah, loop from all final states. Oops, I held it for too long. Okay, super. Now what? Do concatenation, let's say with 0. So 0, 1 star. So I'm gonna cut my, no, copy my NFA down to here. Then how do I do concatenation? So I need, yeah, so I need to bring down my 0 NFA. Then what do I do? Yep, so unfinalize the one from the 0 NFA, and what do I do with it? Good. So I epsilon my way from all previously final states of the first NFA into the start of the next one. Okay? Those 2 finals, yeah. Mm-hmm. They actually will still be final the entire time. Mm-hmm. Because there's no other concatenations. All right, so now what do I do? Yeah, do the union. Sounds like a horrible dance move. 0, 1, do the union. All right, so what do I do here? Well, I first need to copy down my 2 NFA. And if I happen to ask this question, you don't have to do every single step in the middle. This is just making sure that you know how to build up the NFA.
Oh, so we don't have to do the final.
Yeah, you only have to do the final one.
But we have to count all the actual states on.
Yeah, it's applying the method correctly. All right, well, how do I do union here? New start state? Yeah, epsilon my way over to both. So I'm gonna do it in place here for the final one. So if I wanna do 0, 1 star union 2 star, whole thing star, what do I do? Yeah, new start state that's final. Yep, epsilon my way in.
and epsilon your way out multiple all time states.
I'm not going to make them non-final, but it actually won't make a difference here. But I want to modify the original machine as little as possible.
Okay.
So, but I could make them non-final. So, and then I'm going to epsilon my way from all from all final states. Yeah, like that. I think those are the only ones.
So you don't have to make them non-final when you win the star.
No. Yeah. I would just keep it as is and not change it.
Okay.
Yeah, but for correctness reasons, there's no reason to make them non-final or to keep them final. It won't change anything because I can epsilon my way over to the final state. You better not make that start state non-final
Yeah, that'd be wrong.
because you won't have the empty string in this case. But
Okay.
okay, yeah.
Could you do intersection again?
For regexes, NFAs, DFAs, what?
Wait. Oh, you don't do intersection for it.
No,
That's
there's.
why I can't remember.
There is a regex for the intersect. There is a regex for it because regular languages are closed under intersection, but there's no method that we know of or we did that produces it.
It doesn't really make, yeah, okay.
There is a method to do it, but it's quite difficult. But we know that there is a regex for it. Other questions? Got like 2 minutes. I can let you guys go a little early, unless there are other last minute questions. So thank you for coming to my lectures. It was quite fun. I'll see you at the final.